Hello and welcome to my talk Stealing with Style, or how to use CSS to exploit ProtonMail and friends. First a little bit about me. I'm Paul. I'm a vulnerability researcher at Sona, where we build solutions to help developers to write clean code. And part of that is, of course, security. So we try to find real-world vulnerabilities to improve our engine. And yeah, in my free time, I love to play and organize CTFs. And in general, I love to break web things, which is what we're going to do today. So first, I will introduce you to the concept of privacy-oriented webmailers and a little bit of background. And then I will show 3 case studies about vulnerabilities that we found in ProtonMail, Skiff, and Tutanota. And finally, we'll draw some learnings from that. So let's get started with privacy-oriented webmailers. Of course, you might ask, what are privacy-oriented webmailers? So they are privacy-oriented because they use end-to-end encryption to encrypt your emails, and also cryptographic signatures to provide authenticity for emails. Then they are in the web because they run in the browser or in similar technologies like Electron. And finally, they're of course mailers because you can send and receive emails, and they handle HTML emails and attachments and so on. And one thing that's special about privacy-oriented webmailers is that they have some high-risk user groups that other email services might also have, but here some people, just like journalists or political activists, whistleblowers and so on, really rely on the cryptography and end-to-end encryption. And privacy-oriented webmailers share a risk with general webmailers, which is they have to render arbitrary HTML in a secure way. The application is itself built with HTML and all the web technologies, so you have to have a boundary between the email body, the content that can be sent by an attacker, and the application itself. Because otherwise, you are at the risk of cross-site scripting, which can be dangerous. And of course, cross-site scripting in general is less of a threat than, let's say, an RCE on the server. But in the scope of these applications, actually there's more stuff that can go wrong than usual with XSS, because once you exploit the client, you can steal the unencrypted emails. You might even be able to steal private keys because they have to be present in the client in order to decrypt and encrypt emails. And you can impersonate the victim by signing emails or just sending emails from their account. And to to tackle these problems, the 3 case studies that we show have some common security measures that they basically all do the same. So the first one is they do HTML sanitization, which is used to just clean out unwanted stuff from an email HTML body, mostly JavaScript, but it can also be other things like images from somewhere else or maybe some styles or whatever. And this is what it usually looks like. You give some library, for example, don't purify, an unsafe HTML string that can contain whatever, and you get back a safe HTML string that's stripped of any unwanted content. The second line of defense is an iframe with a sandbox attribute, and this is actually an allow list of features. So you will put the email body inside of the iframe, and with the iframe you specify which things can work. Are scripts allowed in this iframe? Yes or no? Are pop-ups allowed to open from here, and so on? And this is what it looks like. You just have an iframe element, you give it a sandbox attribute, and then you put all the directives in that you want to allow, and everything else will be blocked. And the third line of defense is the content security policy. This is also an allow list, but this time for resources. So it will tell the browser where things can come from, like where can the browser load scripts from which server, where can styles can come from, and so on. And it's served as a HTTP response header and looks like this. And it has multiple directives, and we will see later some of them and what it actually does. So let's start with our first case study, which is ProtonMail. I'm sure a lot of you have heard the name. Maybe we have some users here today. But if you don't know it, this is what it looks like. It's just your regular webmail thing where you can have your folders and see your emails. And yeah, it has to render arbitrary HTML, as you can see in this email. So what security measures do they have? They have all the 3 that I just mentioned. They have HTML sanitization, they have a iframe sandbox, and they have a content security policy. And yeah, all these 3 things kind of line up to give a good protection. And as an attacker, if you want to execute JavaScript in the context of ProtonMail, you will have to bypass all of those three. So let's find out how that was possible. First of all, how can we bypass the sanitization? So ProtonMail uses DOM Purify, which is a very popular and probably the best client-side HTML sanitization library. It uses the same parser as the browser, so it's very, very close to what will actually render the HTML after. But what they did is, after sanitization, they changed something in the sanitized HTML, which is a bad thing to do. And what they did is they looked for all SVG elements, and if they found one, they just renamed it to Proton SVG. So the tag name is now Proton SVG. And they do this by creating a new element, copying the children, and replacing the old one. So you might ask, what could go wrong with that? Just renaming doesn't sound too bad, right? So yeah, let's take this payload. Here we have an SVG tag. Inside that, we have a style tag. And inside that, we have an A tag, which is just a link. And it has some attribute with just some data in its value. Maybe you can already see that the data in the attributes value is a little bit fishy, but yeah, for so far, the sanitizer doesn't really see this. So if you sanitize this with DOM Purify, it will say like, yeah, it's just fine. There's no JavaScript in here. It can pass. But after renaming the SVG tag to Proton SVG, something else happens. So if it's parsed after the renaming, you can see that it's parsed differently. And especially, you can see that there's a closing style tag that's now closing this style tag inside of the Proton SVG prematurely, and kind of the image tag comes out, and the error handler would be executed and execute JavaScript. So why is that happening? As it turns out, inside of an SVG element, there are slightly different parsing rules than in regular HTML. So once the tag is still named SVG, it's, all the child elements are parsed with SVG parsing rules, but after the renaming, they are parsed slightly differently. And as you can see in SVG parsing rules, a style tag has like child elements, but in HTML rules, they have raw text content. So in HTML, the first occurrence of the closing style tag byte sequence will close the style tag, which is the part of the differential you see right here. Okay, nice, we bypassed the sanitization. So next up is the iframe sandbox. The first directive that they have in the iframe sandbox is allow same origin. This is just used so that the outermost frame can put stuff into the innermost frame, but it also means that it could go the other way around. If the iframe would execute some JavaScript, it could access the top frame and access everything in that DOM. The next one is allow pop-ups. This just means that if you click on a link inside the iframe, a new tab or a pop-up can open, which is, I don't know, very usual for email applications. If you have a link in your email, you might want to click it. And nothing bad happens here because the iframe sandbox is inherited to that new tab. So everything that does not work in the iframe will also not work in the new tab. And then there's the third directive, which is allow pop-ups to escape sandbox. And it does what it says. This means if a pop-up is opened, the site in that pop-up or in that new tab can do whatever it wants. So if we could somehow do something fishy there, we might be able to go back through the iframe and then to the topmost frame and again access the sensitive data. And then I noticed that if you're using Safari or any other WebKit-based browser, they have a little extra clause where they just allow scripts in the iframe, which is of course nice for exploitation, because in that case, once we bypass everything else, we can just execute JavaScript and directly access the top frame. So yeah, what we're going to want to do for exploit is, if we're on Safari, we can just include a script. And for all the other browsers, we have to open like the rest of the exploit in a new tab, which then escapes the sandbox. Okay, we got that done. So the third line is the content security policy. The first directive here is default source self, and this is just the fallback for all the other directives, or if they're not like specified. And self just means, stuff can come from the same server, the same origin that the page came from, which is usually a pretty safe thing. So doesn't help us much here. The next thing that we can see is they allow inline styles. So some CSS, you can write it inline in a style tag. And they also allow to load images from any HTTPS URL, which is common for HTML emails. All your marketing newsletters probably contain a lot of CSS to look nice, and they also load some banner images from somewhere else, so the email is not 20 megabytes. So nothing too fishy here as of now. But then we see, okay, for scripts, they allow scripts to be loaded from blob URLs. So looks good. Maybe we can load our final payload from a blob URL. That's the plan for now. But let's just look at what is a blob URL, in case you're not familiar. So a blob URL is a thing you can create from JavaScript within a browser, and you give it some content, this HTML right here, and a content type, text HTML, for example, and then you just call some function, and what you get back is a blob URL. And it looks like this. And as you can see, it contains an origin, which is the origin of the page that created it. And then it contains a random identifier, which is randomly generated. And two things to note about blob URLs is they're very short-lived. So once the document that created it gets unloaded by reloading the tab or closing and reopening it, all the blob URLs that were created in that session will become invalid. And what's also important is it inherits the content security policy of the page that created it. So in this example, we have some HTML in the blob URL, which would get loaded when you browse to that URL or fetch it. But the CSP of the surrounding page that created it still applies. So yeah, if scripts can only be loaded from there, then it also applies to the blob URL. Okay, now let's see how we could craft one so that we can then use it to load a script. This is how attachments and especially inline images work in ProtonMail, and it's pretty similar in all the mail clients. So if you want to include a cute picture of a cat inside of your email, not as an attachment, but inline, then you will have an image tag that has a CID source attribute with some ID. And then there's an attachment that has a content ID header, which is matching this value, and also a content type and the content. And when ProtonMail renders this, they just take the content and the content type, create a blob URL out of it, and put it into the source attribute of the image tag. So, okay, now this blob URL appears in the DOM. And what if we send, instead of a cat image or any image at all, just our payload HTML or JavaScript file? Well, ProtonMail will happily create the blob URL again, and yeah, we have this. So the further idea would be, okay, now we can create a blob URL, we somehow need to get it, and then we can use it to bypass the CSP. But how do we get a blob URL for any attachment? And here I had to become a little bit creative. There were known tricks that unfortunately didn't work here. So there's, for example, ways how you can use fonts or styles that you load from another server to leak certain values from a DOM to an attacker server. But we couldn't use fonts from anywhere, and styles could only be inline and not come from somewhere else. So yeah, we had to see how we could do it anyways. So as a small reminder, inline styles plus images that can come from any HTTPS URL had to be used to create some kind of a leak. And here's how that works. So one thing that I used was CSS attribute selectors. This is one example. And it just selects all the image tags that have a source attribute, which contains the string AB. And we can create kind of an oracle with this, where we can basically say, like, if this attribute of that tag contains a string that we are looking for, then send this request to the attacker server, and the sending the request works by just specifying a background image with a URL, and then when rendering, the browser will just fetch this image because it has to show it. So then the attacker server would know, okay, there's an AB somewhere in this attribute value, or CD, or whatever we're trying to looking for. So to make this useful, we had to create like around 5,000 of those selectors for all the 3-character combinations that could occur in a UUID, because the UUID is the random part of the blob URL. Everything before that, the origin, it's known. So we just need to leak this UUID. So in theory, we create selectors for all of these, and some of them will match for all the things that are in this particular UUID. And then for every one of those, a request will be sent to the attacker server. But okay, we get a lot of requests. It's like only snippets. How can we put it together? Let's look at this example of a blob URL that starts with the UID like ABCD. And now, if the browser renders this, it will go through all of the CSS selectors that we created. And the first one that will match is ABC. Yes, ABC is in that blob URL. So it will request the ABC URL from the attacker server. And now the attacker server knows, OK, ABC is somewhere in there. Then the browser will continue to render. And it will see, OK, BCD is also in there. It's at offset 1. Let's send also a request for that. And now the attacker server knows, OK, ABC and BCD is in there. So what it can do after it received all the requests, it knows, OK, because it's all 3-character chunks, they will have some overlap, like this. BC occurs in ABC and BCD. So it can use this overlap to just stitch together the original blob URL, and then it knows the URL. But there's one problem. You can only have one background image per element. So what we are trying to do to send the request to the attacker server is to use this background image. But if multiple matches happen, the first one will be overridden. And since the browser will render this in one go, it will first resolve everything and see what overrides which directives. And then at the end, it will only request the images that it needs to. So with this, it would only request one image and not all of the ones that would match. But there's a solution, and I say this very easily, but this was me reading through CSS spec and functions 2 days straight and losing my mind. But what I found is there's the crossfade function, which takes 2 images and a percentage, and it will then overlay them. And for the images, you can either directly specify a URL, or you can recursively use the output of another crossfade function. So what we can do is we just nest a lot of crossfade function calls, and at the root of that nested calls, we will pass URLs as the parameters. And now we can use as many URLs as we want for one element, because in order to render the whole thing, to overlay all the images, the browser, of course, has to request all of them first, and then it can render them. OK, let's take a step back and combine all this leak process. So first, we create a lot of these selectors, and for each one that matches, where this particular 3-character combination is inside of the blob URL, we set a CSS variable to a certain value. Then at the end, we have one selector for this image that combines all the values of these variables into one big crossfade nested call block. And that's it. This will cause all the write requests to go to the server, and then the server can stitch it back together. Very nice. Now we have a blob URL that has a content of an arbitrary payload that we defined and an arbitrary content type that we defined. Very good. So let's look at how we can put the whole exploit together. So as a stage 1 email, we will send this one. It has an image tag that points to this attachment, which is our payload, and of course the style that will leak all this stuff back. And once the victim opens this email and just views it, the browser will render it, and with the CSS leak technique that I just described, all the blob URL snippets will be sent back to the attacker server. The attacker stitches everything back together, and then the attacker has to send a stage 2 email just in the follow-up email thread, which then, for Safari, for example, just includes this blob URL as a script tag. And once the victim views this, it's game over, and JavaScript should be executed. So let's see how this works in real life. So this is a recorded video. Of course, ProtonMail is a hosted service. I cannot just downgrade their version to show my demo. So we will see how that works right here. On the right, you will see the attacker script. It will just send the stage 1 email, and then the victim refreshes their ProtonMail, and a new email will appear. That's it right there. Then, there's nothing suspicious in it, some embedded image, but on the right, you can see that the blob URL was received and the stage 2 email was sent. So, everything was stitched back together. Now you see the new email appear, and upon watching it, the alert triggers. OK, let's look at the disclosure process. All this happened in last summer. We sent the report. Some days later, they pushed the fix to the public repo. Then some days more later, they awarded us with a $750 bug bounty, which was nice. We could give it to charity. And then roughly 1 month after our report, they deployed it to production. So pretty good time frame. I would just recommend not pushing the fix before, or like much more before deploying the actual fix, because people that know these kinds of attacks could have seen the commit and could have reverse engineered what it was for. But so let's look at the next case study. This is again cross-site scripting, but this time in Skiff. And Skiff, again, a end-to-end encrypted email service. It looks like this. It's, I think, less known than ProtonMail, but it's basically a similar service. And they also use similar security measures. So they again have sanitization, iframe sandbox, and content security policy. So we have to do the same thing again and bypass all of those. And again, they use DOM Purify, which is very good, but also again, they modify something after they sanitize their HTML. And what this does is it looks for elements that have a certain attribute, and then they will just insert a empty div tag just before that element. So let's go through this step by step to see why this is bad. So this is again our payload. It looks pretty much the same like the last one. It just has this data injected ID attribute that this function is looking for. So this again passes sanitization just fine. They, in this case, sanitize the HTML and don't return a sanitized string, but like the sanitized DOM structure. And then afterward, with their function, they just inject this div tag, which is now the first child within the SVG tag, and it's just there. It's empty. Nothing much happening for now. But then you notice that a div tag is not really allowed in SVG tags. It's an HTML tag, so it should be in the HTML realm and not within an SVG element. So when the HTML gets reparsed, and this happens just before rendering, they take the inner HTML of the sanitized DOM, and which serializes it to a string, and then they set it to some else's elements inner HTML, which parses it again from a string. And this time, the HTML parser of the browser will see, my SVG tag has a contained div tag. That's not really allowed. Let's move this div tag outside of the SVG tag. And with that, everything after the div tag gets also moved outside. And then the same parser differential between how style tags are parsed within an SVG tag and in regular HTML are just triggering again, just as I explained it for ProtonMail, and JavaScript gets executed again. Next up, the iframe sandbox. This is also pretty much the same, just without the Safari exception. So in this case, we definitely have to open our exploit in a new tab in order to execute some scripts. But it will still work. And finally, we have the content security policy. Again, they have a default source of self, which is pretty secure. And then for scripts, they allow the eval function, which is just, you give it a string, it evaluates JavaScript. And without this directive, if you have a CSP, then it would just not work. It would throw an exception. And they also allow scripts to come from hcapture.com, among other things, which is just a capture site, I guess. And it's just like reCAPTCHA and all the other captchas that you know. But when I tried to look at this domain to maybe find some script gadgets in there that could help me bypass the CSP, I noticed that it's hosted behind Cloudflare, which is also nothing unusual. It's probably the most used reverse proxy in the world. But one interesting thing that some people don't know, apparently, is that all Cloudflare sites, all sites behind Cloudflare, they have this new path, CDN CGI scripts, under which Cloudflare serves some JavaScripts. I think it's to show they are like you're being redirected site. But apparently, in one of these scripts that are served from there, there's a known gadget that can be used in exactly this case, where you have an eval allowed in your CSP and a domain that serves these scripts. And then you can combine it and just bypass the CSP by creating an HTML structure that will then be parsed. And in the end, JavaScript will be executed by this gadget script. So this is what it looks like. Unfortunately, I don't have the time to go into it. but I have some links there. You can check it out later when the slides go online. They use some DOM clobbering, and I didn't come up with this. I just found it. It's very cool, so be sure to check it out. But we have to continue. So yeah, as Skiff is pretty similar to the ProtonMail thing in terms of security measures, and because of that, also in terms of exploitation, we can already see how it works. So we again do a blob URL leak. Although we didn't have blob URLs allowed in the script source, we do this to have a blob URL that will then be opened upon click. So the content of the blob URL will be what is rendered in the new tab that's opened. And yeah, to do it, we again send an email with some style tags and an attachment, leak back the chunks of the blob URL, stitch it back together, and once we have it, we send back a stage 2 email, which in this case has a link. We cannot directly do it. The victim will have to click, but if it happens, then JavaScript will be executed again. So also, let's look at this. Again, this is a recorded video of back from when this was still vulnerable, when I found this. And here you will see that when we first refresh, the first email appears. Again, this is just an innocent email saying hi, nothing much. But in the background, now again, the CSS is being rendered. All the requests are being made to the attacker server. The attacker server stitches back together the blob URL. And then once it has done so, it will send the follow-up email. That should probably happen now, yes. And when the victim refreshes, the next email is there. And now the victim has to click on the link. But now we have the cross-site scripting again. So disclosure with Skiff was very boring, which is a good thing for disclosures. We just sent the report, they fixed it 2 days later, and it was done. Very good. So let's look at our third case study, and this is Tutanota, and especially the Tutanota desktop app, which we first found XSS and were then able to improve it to remote code execution. Tutanota, just like the other two, it's just an email client, so it looks the same. But in this case, it's not running in the browser. Not in your regular browser. It's running inside of Electron, which is just some JavaScript together with a browser shipped to your machine. And the mitigations are a little bit different here. They do have sanitization. They do not have an iframe, so we got that for free. We don't have to bypass some sandbox there. Then there's the content security policy. And finally, after the web part, there's the Electron sandbox that we want to escape in order to directly execute code on the system. So for the sanitization, you know the drill by now. They use DOM purify, but again, they modify the stuff after sanitizing it. This time they use this library to convert all text URLs to link tags that might be in the HTML somewhere. But as it turns out, this library that they use for this parses the HTML itself. And they use a custom parser that's different to what the browser and what DOM purify uses. So let's see again, step by step, what we can do to bypass this and make use of this parser differential. Again, this is our good old payload. You know it by now. There's just one thing differently. We have this I element with an X attribute, and you will see in a minute why. And again, this is just waved through by DOM purify. Nothing suspicious here, at least not to DOM purify. Then in the next step, the Linkify library will parse the HTML. As I said, it's not the browser's parser, it's a custom one. So you will see that the style tag is parsed with HTML rules, which is not correct because it's inside of an SVG tag. And although the image tag appears here, it doesn't get executed yet because this is just in the parsing of the library. It's not being rendered by the browser yet. So, okay, it parses it. And then at the end, after processing all the links that might be there, it will normalize the HTML before serializing it back to a string. And what they do here is they add default values for attributes that didn't have a value before, like this X attribute, or they put double quotes around attributes that didn't have double quotes to make it all look normal like good HTML. But this leads now to a problem, because when all of this is put back together to a string, the browser will now parse it differently than when DOM purify parsed it. And this is because of this one. this one double quote, which now prematurely ends the alt attribute, and now the image tag comes out again, and yeah, the on-error handler is executed. So again, we did it, we bypassed the sanitization. And next up is not the iframe sandbox. As you might remember, there's none in Tutanota, so we can directly go on. And there's the content security policy. So here again, they have a default source of self, which is pretty secure, at least in the web. But what I noticed is, inside of Electron, all of the pages and JavaScript files are served from the file protocol. And the CSP uses self to look at, okay, which origin does the site come from? But an origin consists of a protocol, a hostname, and a port. But for the file protocol, there's no host and no port, so it all boils down to just the file protocol, meaning that with this CSP and stuff being served from the file protocol, all local files on your disk are allowed by the CSP. So maybe we can use this. And yeah, just a little note, Electron is like a nice framework if you just want to build one application, and it will work on all the major desktop OSs. And for the next steps, we will focus on Windows because their exploitation was the easiest, as you will see. So we want to use a local file to load it as JavaScript, but how do we get one? For this, we look at attachments, and for Tutanota, to show an attachment, they get downloaded and decrypted. It's still end-to-end encrypted. And it then, after decryption, ends up in a known location. So in some temporary directory, some subfolder, and then it uses the name of the attachment file. So we can know this location, basically, as an attacker. So the idea would be now, once the victim opens an attachment, and it can be something innocent like a TXT file, then we know this path, and we can just include it as a script, and it should execute. But there's a little bit of a problem here, a little bit of timing, and we have to make the victim open the attachment. So for the timing issue, we use this trick. We use an iframe with a source doc attribute, which is normally you use an iframe with a source attribute and put in a URL that it will load. But with source doc, you just put the HTML right in, and it will render. So the first thing we have inside of that is a meta refresh tag, which will refresh the iframe itself every second. And besides that, we have a script that tries to load this file. So this will refresh every second. Every second, it will try again to load the file from the disk. And once the victim clicks open, it will actually work, because then the file's there and it will load. So how can we make the victim click open attachment? Well, we can use our good old friend CSS to redress the UI a little bit. As I said, there's no iframe in Tutanota, which also means that all the styles that are contained in the email body will apply to the whole UI and not only to the email. And this is good because we can just make the open button really big, overlay the whole UI and make it invisible. And then once the victim clicks anywhere, they click actually the button without knowing it. So having that, we now have a plan to do our cross-site scripting, but from that we want to go to remote code execution. And first of all, we looked at the Electron security hygiene. So Electron has some special configurations that are for security, but they all look pretty good. Context isolation was on, node integration was off, and all the other things were also good. But in order to do the things that it needs to do, the app still has to have a way to write some file to disk when you click Save Attachment, or if you click Open Attachment to open it. So it has some IPC calls that are being done between the web part and the main part of the Electron application, and the main part can then access the system. So we have this write file one and the open one, but when opening files, there's a block list. We can't just send a .exe attachment, and once clicked, it will execute. But we still want to use this. We want to use the write file IPC call to write an executable to disk, and then use open, which uses the shell execute W function to open it, and which will run the application on Windows. So let's see how we could bypass the block list. This is how it looks like. It's just a big array of known bad extensions. There's about 20 of them, and there's probably a way to bypass this if you're good with Windows and know some weird extensions that nobody else knows about, but I didn't know any. I tried stuff from the web and nothing worked, so I had to look further. And this is how they take the file extension from a file path. They use the path.xname function, which is a Node.js library function. And this is how it works. So if your file is called foo.exe, this will return .exe. And this will be blocked because it's in the block list. And all of this is good because foo.exe should not be opened because it might be dangerous. If your file is only called foo, it will return an empty string because there's no extension, there's no dot in the file name. And this is fine, it's not blocked, but Windows wouldn't know what to do with this foo file anyway, so no problem here. But there's an interesting edge case where if you call your file only .exe or .something, the file extension will be empty. My guess is this because it thinks it's like a dot file on Linux or whatever, but this is very interesting for us because a .exe file that's called just that will be happily executed by Windows if you double-click it or use the open call, but it's not in the block list. The empty string is not in the block list, right? So again, here we have a bypass. And the funny thing is, this is actually well documented in the documentation of this function, but who reads documentation anyways? So I only did it to find a bypass. So let's put it all back together. First, we send an email that includes this iframe that reloads itself and some style to make the open button real big and invisible, and as an attachment, our JavaScript. Once the victim opens the email and clicks anywhere, which actually clicks the button, the JavaScript will start to execute, and once it executes, it will use these two IPC calls to actually run code on the system. So again, let's see how this works out in real life. And again, this is a recorded demo. At first, I thought I could just use the old version of the client because it's just an application you can download. But what they actually do is they prevent old versions of the client from working. So the backend will just reject it. And also the API changed, so I couldn't make it work. So we have to take this old video. And the victim will just reload and see, oh, there's an email. Let's look at it. And I will pause here because you can see the email is empty. And unfortunately, in this proof of concept video, I didn't use the CSS make the button big and invisible technique. But you will see better how everything works. So the victim will just click on open on this txt file. And the txt file opens. And next to that, we have the calc. OK. Disclosure timeline again. We sent the report last summer. One day after, they confirmed it. One day after that, they released a fix. And 1 month after that, they did something that was really nice. They, from their own motivation, made a blog post on their blog that said, like, hey, we had this vulnerability. This is roughly what it is about. This is what risks there were for users. And this is how we mitigated it. And they're planning to harden our application in the future. So this was really nice to see that they're really open and transparent with their security and gives me a lot of trust in their position towards security. OK, now let's wrap things up. We've seen our 3 case studies and what can we maybe learn from them. So the first thing is, as a web exploiter, CSS should not be overlooked. OK, you want to execute your JavaScript, but as we have seen, CSS can be your friend, either by leaking some stuff or by making it easier to trick a victim into doing a certain user interaction. And there might be some more fun in the future. There are some things that are being drafted in the CSS spec right now that could make all these leaks easier in the future with just one request instead of all of these that have to be stitched together. So let's look out for that. The second point is modern mitigations do actually work. They make exploitation harder. As you have seen, all the exploits needed some user interaction, 2 emails being sent in a row, you can't reload the page in between, and so on. So all the mitigations, the content security policy, the iframe sandbox, the sanitization and everything, it still kind of worked and made everything harder, and it's not like you receive an email and you're directly pwned, which is also a good thing. And finally, and I do want you to really remember this, is do not touch or modify your data after sanitizing it. It will come and haunt you. Thank you.